Well, welcome to question 3 from the end of chapter 12, which is all about solid-solid mixing. There's a lot of calculation in question 3, but let me take you through the question to start with. It's a binary mixture of powders, free-flowing powders, powder A and powder B. We're going to set up powder A as being what we call down here component P. Okay, that is going to be equal to our powder A, and our powder B is therefore going to be component Q. We have the Poole equation down here for the calculation of the variance, expected variance from a random mix. That's what the R stands for, the random mix. So we've given proportions, mass proportions 2 to 3 of A and B, so that means that P is going to be equal to 0.4 and Q is going to be equal to 0.6. That's the proportions 2 to 3. Densities, I'm going to say density of component A is 3,500 kilograms per meter cubed, but I'm going to use 3.5 grams per centimeter cubed, using CGS units, grams per centimetre cubed, and density of component B is therefore going to be 2.5 times, grams per centimetre cubed. The only other aspect of what we have here is the scale of scrutiny, which is 4 grams, so M equals 4 grams. So we know the value of P, we know the value of Q, we know the value of M. It's just these two things here, WP and WQ. And these are the average weight, average mass really, average mass of a particle in component P or A, average mass in component Q, or as we have here, B. So this is the P material, this is the Q material, and you'll see that we're actually given a cumulative graph, a cumulative function rather. Most importantly, note that the cumulative function is defined in terms of millimetres, and if we're going to use CGS, as I have been down here, then clearly we need to convert the millimetres to centimetres before we can do our calculations that we need to work out the mean average particle mass using this distribution data. So it's a little bit tiresome in the calculations, but for the sake of completeness they're here, and I'll go through them in fairly quick detail, just make sure I'm not missing anything. First of all, what do we need to calculate? The average particle mass component P is here. The average mass component particle Q is here, and as I said, we're using A for component P, B for component Q. So straight away I'm assuming spheres, because we have just here a volume shape factor for spheres, pi over 6. We have the density. Now we would like to just have x cubed just here, the average particle size cubed, but we're not given the average particle size, so what we can do is use the distribution, and this is technically sometimes what's called the weighted mean particle weight. Really what it should be is the mass weighted mean particle mass. So in other words, WP should be the mass weighted mean particle mass. Well, why is it mass weighted? Because N3x is there and not N0x. If that was N0x, that would be number weighted, but having N3x there means that we're weighting the result to the mass distribution. So the weighted bit in the middle, the weighted, mean particle weight. The weighted bit in the middle is really meaning biasing. We're using the relative to the mass distribution. So it's the weight of, or mass rather, of a particle as biased to or relevant to the mass distribution. And it's the same issue here. We have m3x just here, and that will give us, bearing in mind that basically it's density times volume, that should give us a particle size in terms of particle mass, sorry, in terms of grams. Okay, well, we have the functions for the particle cumulative functions, and going back to my earlier comments, the first step is to convert from millimeters to centimeters. Now that's straightforward for our limit. What about the equation? Well, actually all you need to do there is consider the constant and what the constant needs to be changed to enable the upper limit to be equal to 1, because we know uppercase n3x equals 1 at x equals the upper limit. So that's certainly true here. If we put in 0.5 microns into this equation, you'd end up with 1, square root of 1. So logically all we have to do here is change the 0.5 to 0.05. And again, when we put in this limit into this equation, we end up with what we should do, which is n3x equals 1 at the limit. Then we need to differentiate, because we know this expression, this relation between the cumulative function and the differential function, and we need little n3x. We need the differential function in our weighted equation. So we need to differentiate the equation, which for component A is, well, this is just splitting out the constant to the power minus 0.5, so it's coming from this equation here. Then as we're going to be differentiating, that's going to leave x to the power 0.5, which of course differentiates to 0.5x to the power minus 0.5. A little bit more algebra comes up with this equation that we've highlighted down here, which is the equation for little n3x, the differential equation for n3x, which is 5 over x to the power 0.5. So we've got the equation there for little n3x. Similarly for B, move that over a little bit. Yep, that's what it'll do. Similarly for B then, again we start off with the cumulative function, which we first of all need to convert to being in the units of centimeters from millimeters. Same principle, we're only really talking about changing the constant. That has to come down to 0.025 for the upper limit to make any sense, and then that gives us the equation for the differential function down here, the n3x equation. And the n3x equation, differential equation, comes from differentiating the cumulative equation, and that's basically a fairly straightforward differentiation, this one, because clearly we've got 1 over 0.025 all squared times by x squared, and then of course we differentiate x squared to simply be 2x, and by the time all the collecting together of terms comes out, the answer is simply 3,200 times by x, where this is our limit, where x is less than 0.025. So excellent. We have our two equations then for little n3x, that equation for component A, this equation down here for component B. Right, we can now use these in our in our it looks horrendous, it really does, but it's alright if you just keep logically going through it. So here is our equation for the mass of the average mass of a particle in component A. We've substituted in our equation just here for n3x. So don't forget that this bit here is the n3x that we've just been talking about. And then with the integration, you'll see the 3.5 is the mass there. The root 5 comes from the 5 to the power 0.5 in the integration just here, and the rest of it hopefully makes some degree of sense. We end up with x to the power 2.5 in the integration, which is then integrated to give you x to the power 3.5. And if you work through there and get all the numbers out, then the mean particle mass of component A comes out at near enough 3.3 times 10 to the minus 5 grams. We've got to do all that rigmarole for component B, which we call WQ. Same principle, and in this instance we come out with a slightly lighter particle. We come out with 0.82 times 10 to the minus 5 grams. So these are the two missing components that we need in our pool equation, because we were given the distribution rather than the average values, so we've had to use the distribution and do first of all the differentiation to come up with the equation for n3x, and then the integration to come up with the mean particle size, mass. Okay, so these two masses are now ready to go into our equation, our pool equation, which we have down here. And I've just made life a little bit easier by taking 10 to the minus 5 out just here. So this was WP term, obviously times 10 to the minus 5. This is our WQ term, again times 10 to the minus 5, which has just been taken out of the brackets. P was 0.4, Q was 0.6, and we know the scale of scrutiny is 4 grams. It gives us a variance, don't forget this is variance, gives us a variance of 1.37 times 10 to the minus 6. We obtain the square root of the variance to give 1.2 times 10 to the minus 3. Right, and that's what we'd expect if we have a random mixture. That's the random standard deviation mixture quality when it's completely mixed. We're not really expecting anything better than that, although that's actually quite a good value. Let's put this into context now. We know that P is 0.4. Okay, so here is 0.4, and we're going to work on the principle that the samples drawn at random from our mixture should follow a normal distribution. So some of the samples will be smack on 0.4, some of the samples will be less than 0.4, some of the samples will be more than 0.4. But our specification says that in the question we're expecting 0.4 plus or minus 5%, and 5% of 0.4 is 0.02. So in other words, we're expecting P to vary between 0.38 and 0.42 to be in specification. That's the allowed variation. We're not told any confidence, we're told that that should be the variation. And we know from our standard deviation, if we work on the 3 sigma value, then it's probably easier to add rather than take away, so let's focus in on this side. We would expect 0.4 plus 3 times 1.2 times 10 to the minus 3, which is 0.4. That becomes 3.6, doesn't it? So that becomes 4 plus 0.0036. I mean, if we're going to round it, we can call that 404. So that becomes 0.404. So only one in 1,000 samples will be higher than that value there, 0.404, which is still well below the 0.42 threshold. And similarly, you could apply the same argument down here because of the symmetry of the normal distribution. So the question really becomes, what is the difference? Instead of 3 times the standard deviation, how many times the standard deviation do we have to go to before we're at a value of 0.02, which is the difference between the upper limit and the mean value? And that is going to be massive. It's going to be many, many, many sigmas. It'd be possible to go and look that up in the statistics tables, but it's a lot more than 3. So in other words, this distribution is quite a tight distribution. It's going to go from 0.396 to 0.404, with just 1 in 1,000 higher than that value and 1 in 1,000 lower than the value. But even the 1 in 1,000 is well below our told specification. So our confidence of meeting this specification is really good. The actual variation is going to be something like 1 in 10 to the 7 or 8, something in that sort of order. So we can live with that. You know, we know that statistically there will be some product that is out of specification, but it's going to be 1 in a vanishingly small amount because our standard deviation is so low. So that gives us good confidence with this product, provided we can get the right mixer to do the job. We should be able to mix this material really well, these two components. Okay, bye.